Hi, everyone. This is John Mandrola from the Heart.org Medscape Cardiology, and I'm here in Barcelona, Spain, at the European Society of Cardiology meeting. And I'm really happy to have Professor John Eichelboom from Hamilton and McMaster's University. Dr. Eichelboom is an expert in anticoagulation, and we're going to talk about this new and exciting thing going on with factor 11 inhibition. Welcome.
Thanks very much, John.
Tell us what exactly is factor 11 and why is it important?
Well, it's conceptually very simple. Factor 11 is a clotting factor. It sits high up in the clotting pathway. And some of us remember medical school 2 pathways, but we needn't get into the details. We've ignored factor 11 for many years, but now there is a new insight that perhaps it's the ideal target for a new anticoagulant.
The problem with anticoagulation, isn't it, that everything that reduces thrombosis also increases bleeding? But there's something special, at least the idea here.
Exactly, and that's where the 2 pathways come in, because factor 11 sits on this contact pathway, and it doesn't have a lot to do with controlling bleeding. So factor 11 is not important to get hemostasis, but it is critically important for thrombus formation. So we could leverage this dissociation. If we target 11, we can stop a pathologic clot from forming, but still allow normal clot formation.
This sounds like the Goldilocks type of anticoagulant, no?
Indeed. And we've heard it before in the development of antithrombotics. We love to hear about molecules that are going to do the right thing and have no side effects. It remains to be demonstrated that targeting factor 11 will achieve this holy grail of antithrombotic therapy. We need the trials for that.
So wait a second. Are you telling me something that makes sense may not work clinically?
Indeed. Well, lots of things make sense. We deliver a hypothesis. That's why we do the science. The world loves new hypotheses. We as clinicians, you as a clinician, love these new concepts. But unless we do the proper trials, the randomized trials, we don't know the answer. We don't know the truth. And many of our hypotheses are ultimately proven to be wrong.
Yeah. So tell us more about how something can stop clot formation or block thrombin formation, so-called amplification,
yes,
but yet not affect. This is strange to me.
Okay, well, let me use an example. If I injure myself in a motor vehicle accident and I get a crush injury to tissue, there is a massive amount of thrombin generated. One of those 2 pathways we talked about, the tissue factor pathway, produces an enormous drive to thrombin generation, and we form clots. However, it's a completely different story when we have an acute coronary event, because there we have a plaque embedded in the wall of a vessel that ruptures. We get a small amount of thrombin generation. That thrombin is insufficient by itself to cause an occlusive thrombus. That thrombin needs to be amplified so that we can create or generate enough thrombin to cause a thrombus. And that amplification step requires factor 11.
And how did one figure this out? I mean, I was reading that it was almost a fortuitous discovery.
Indeed. Well, the best information on factor 11 actually comes from hemophilia C. And most of us don't see hemophilia C, but that's the inherited form of factor 11 deficiency. People who have factor 11 deficiency hardly ever bleed. Now, there are some exceptions. We don't fully understand it, but very low risk of bleeding, even if their factor 11 level is 1% or 2%. But they're relatively protected against thrombotic events. And that really drove the idea, if we could selectively target this lower the factor 11 to very low levels, that we'd get our hemostasis, we'd have our cake and eat it.
Right. So there's a number of ways to go about this, isn't there? There's different drugs and different mechanisms. So give us an overview of what we're talking about.
So the three big approaches, the three most common approaches. One is with an antibody, and the antibody basically binds to factor 11 and gets rid of it. So we lower factor 11 levels. The second is this exciting technology, an antisense oligonucleotide, a piece of genetic material that stops the cell from producing factor 11. So like the antibody, you lower the levels down. And both of these two are parenteral agents. They're given by injection. The third, and perhaps the most exciting, is the small molecules that are taken orally, and there are several companies that make these, and they target not factor 11, but factor 11A. It's a bit of a nuance, but they target the activation product of factor 11 when it gets fired up.
And I remember from the American College meeting this spring, there was a study that showed some in atrial fibrillation that showed some potential positive signals in terms of lower bleeding, not enough thrombotic events. And give us a view of like what's going on in the trial world now. I think we're in the phase 2 studies level, aren't we?
Well, there's a large number of companies. Firstly, there are a large number of molecules. Even within each of these classes, there are several different molecules, and many of the trials, the phase 2 trials, are reading out at around this time. The big picture summary of the phase 2 trials is, yes, we're seeing low rates of bleeding, not always as low as we'd expected, but generally low rates of bleeding. But the trials haven't been powered for clinical events. And so we're still not sure how effective these drugs are going to be to prevent our stroke, our myocardial infarction, and our cardiovascular death. So for that, we need some big phase 3 trials, and they're going to happen very soon.
Do you think that the phase 2 trials that we are seeing now are enough to warrant or have any optimism about the phase 3 trials? And the reason why I ask is because isn't the direct acting oral anticoagulants are pretty good?
That's the big question. You've, as usual, I'm a follower of you. You asked the right questions, and I think that's what everybody is asking. Will the newer agents produce a sufficient reduction in bleeding? And of course, will they be effective to warrant them replacing these wonderful drugs we have, dabigatran and rivaroxaban and edoxaban and apixaban? We have an astonishing array of effective anticoagulants. I just want to say one thing about this. If we look at the big atrial fibrillation trials, DOACs versus warfarin, we forget that 1 in 10 people each year in all of those trials, whether on warfarin or a DOAC, had bleeding. 1 in 10. Now, major bleeding, much less common. Bleeding is still a big issue. And where bleeding is most important is the patients who we currently don't treat because of bleeding concerns. So it's not all about head-to-head comparisons. With the emergence of DOACs, we expanded the market. We still have a quarter of our patients with atrial fibrillation who don't get anticoagulated, mostly for bleeding concerns.
So even if this factor 11 strategy is equally good thrombotically, if there was less bleeding, that would be a clinical advantage.
That would be a clinical advantage, but there's definitely going to be a price tag. So we need to see a big reduction in bleeding. And that's where the big question is, will we see less bleeding? I suspect we will, based on what we know so far from the early studies. Will we see efficacy? Where we need the phase 3 trials to demonstrate that. Will the advantages be big enough that the extra cost of these new drugs will displace the other ones?
Excellent. This was extremely helpful in helping me understand this, and I'm really grateful that you came on. Thank you very much.
My pleasure. Thank you.